Welcome back to Mentoring Maya. In our last session, we worked through the mechanics of mapping clinical intent directly into database design. Today, we take that mapping process and apply it to one of the most sensitive areas in any oncology trial, designing tumor forms strictly aligned with RECIST 1.1 guidelines. Tumor assessment is more than a standard data collection module. The data you structure here directly calculates the objective response rate, progression-free survival, and duration of response. If your tumor data structure is weak, those endpoints are instantly at risk. No amount of downstream programming can patch a poorly designed tumor data flow. Before you place a single field onto an eCRF, you must understand the exact flow of RECIST 1.1. This diagram illustrates that chronological logic. You start by identifying target and non-target lesions. Then you track measurements over time, monitor for the detection of new lesions, and funnel all of that data into a final calculation for overall response. Database builders who skip learning this logic end up with fragmented designs. They build isolated forms that fail to communicate with one another, making the data nearly impossible to analyze. To design an effective tumor form, you have to work backward. You look at how the final clinical response is derived and build the architecture to support that exact calculation. A common trap in oncology data management is the attempt to force all tumor assessments into a single, massive eCRF module. We solve this by breaking the eCRF apart into 4 logical modules: baseline, on-treatment, new lesions, and overall response. The baseline captures the initial state, lesion IDs, locations, and baseline measurements. Next, on-treatment chronologically tracks measurement updates, changes, and assessment dates. This modular approach reduces the cognitive load on site users and ensures the logic pathways required for response derivation remain intact. Let's focus strictly on the rules for target lesions. These are the measurable indicators of disease. During the baseline visit, the investigator must select and uniquely identify each measurable lesion so it can be monitored accurately throughout the trial. Your database needs specific fields: lesion ID, location, method, diameter, and date. Crucially, baseline identification must link directly to follow-up visits. That persistent link mathematically proves if the disease is progressing or regressing. If that traceability breaks down between visits, the fundamental response calculation fails instantly. Non-target lesions require a completely different approach. Because they represent unmeasurable disease, applying the complex tracking logic of target lesions will only create errors. For non-target eCRFs, you drop the numerical input fields. Look at this simplified table. It relies on standardized dropdowns to track whether a lesion is present, absent, or has progressed. Then we have new lesions. In longitudinal trial data, a new lesion is the most critical trigger point. Properly recording the appearance of a new lesion inherently determines total disease progression, regardless of what is happening with the existing target and non-target lesions. You only need a few vital data points here: confirmation of its presence, the date of detection, and basic descriptive details. Overcomplicating non-target data or failing to strictly structure new lesion capture guarantees inconsistent progression classifications down the line. All of this data relies on strict timing. Clinical protocols define specific intervals for tumor assessments, and those schedules must be adhered to. Your database structure must capture precise assessment dates and contain logic to cleanly handle scans that are missed or delayed. The final architectural decision depends on your protocol. Will the overall response be investigator-assessed or derived by the system? If investigator-assessed, your structure must employ controlled terminology, aligning perfectly with raw lesion data. If system-derived, algorithms require flawless, structured capture. Any unlinked variable will instantly throw an error and halt calculation. If your database architecture does not align perfectly with the chosen derivation strategy, it creates a massive reconciliation burden that takes weeks to resolve. To build a clean eCRF, you also have to know what to actively avoid. Let's review the common mistakes that routinely degrade oncology data. The overuse of free text fields is a destructive habit. An interface full of unstructured paragraphs makes systematic response derivation impossible. Other major traps include failing to mandate assessment dates, leaving baseline identifiers unlinked, and neglecting the specific logic required to capture new lesions. Remember that clinical site users are operating under severe time constraints. Clarity and simplicity in your forms are mandatory requirements, not optional features. When forms are complex and error-prone, the quality of the data is permanently degraded the moment it is entered. Exceptional tumor form design enforces the consistent tracking of disease over time, transforming individual data points into a clear, longitudinal record of progression. The blueprint is clear. Thoroughly understand RECIST, modularize your forms, guarantee lesion-level traceability, and strictly align your data points with the assessment timing. Executing these steps perfectly is the most effective way a clinical data manager can guarantee the integrity of a trial's endpoints. In our next episode, we apply these rigorous structural principles to safety data, diving into adverse event design with CTCAE. This content is provided for educational purposes only, reflects general industry practices, and is not affiliated with, endorsed by, or representative of any organization or official standard.